Good evening and good morning, everyone. I'm Jinfeng Zhang, a researcher from Recon AIP. Today, I'm going to host the first TrustML Young Scientist seminar. Before that, allow me to briefly introduce the Recon Center to our valuable guests. The full name of the Recon Center, Recon AIP is the Recon Center for Advanced Intelligence Project. AIP was founded in 2016 as the research center for the MAX AIP project. AIP Center conducts Japan's leading AI research, which is headed by Professor Sugiyama. AIP aims to enhance the AI fundamental technology and its real-world applications. We encourage the collaboration with various researchers and engineers in the related fields. We would be very grateful if you could visit us in Nihonbashi office in Tokyo in the near future. Next, allow me to introduce our valuable guest, Dr. Qin from Fudan University, and later Sven Gower from DeepMind, London. Dr. Qin is now an associate professor at the School of Computer Science in Fudan University, Shanghai, China. Before that, she was a postdoctoral researcher at the School of Computing in the National University of Singapore, working with Professor Cai Da Cheng. She received her PhD degree in computer science from the City University of Hong Kong in July 2018, supervised by Professor Yang Zonghua. Her research interests lie in the area of robust AI, multimedia content analysis, and deep learning. And actually, Dr. Qin won the Best Paper Student Award in ACM Multimedia in 2016 and Multimedia Modeling in 2017. In 2020, she was selected to the Shanghai Pujiang Talent Program. Let's hugely welcome Dr. Qin to give us an exciting talk. All right, Dr. Qin, you can proceed to share a screen right now. Yeah.
Let me share my screen. Share screen. Okay.
Okay.
So can you hear my screen now?
Yes, I can see your screen and hear your voice.
Okay. Firstly, thanks very much for the invitation from Jinfeng and Professor Moriyama. And I'm very glad to give this talk and share some research progress in my group. And good afternoon, everyone. I'm Jingjing Chen. So I'm very glad to give this talk. The title of my talk is Adversarial Attacks on Video Recognition Models. So here I changed the title a little bit because I include one word for the white box attack. So first I will give a brief introduction on the background. So recently, the deep-based video models have achieved a remarkable success in a series of tasks. For example, like the action recognition, object tracking, autopilots, video surveillance. So take the video recognition for examples. So with the recent developed vision transformers, the recognition accuracy, the top one recognition accuracy on the connected 600 data sets can be as high as 90%, and also more challenging data sets. For example, like the something to something data sets with a self-supervised learning method, which pre-trained on the Kinect 400 data sets, which is called the masked feature prediction. It can achieve the top one accuracy at 75%. So as can be seen, the recognition performance. So these video recognition models are rather high now, which makes the video analysis models can be used for many real-world applications. So the question is, are these video models really safe? And the recent studies have shown that the video models are vulnerable to the adversarial examples. So as a result, it raises the security concerns in the real-world applications. And here I show several examples. For example, by wearing the clothes with a specific adversarial patterns, it can mislead the video object detection models and make it cannot detect the person here. And also by adding the human inceptible noise to the original videos, they can mislead the video recognition model from predicting the video as play badminton to play cars. So actually, it arose the security concerns on the video models in real-world applications. As a result, it has attracted a lot of research attentions. So on the one hand, studies adversarial video adversarial examples helps to discover the security issues in the video recognition models and help people to propose the defense mechanisms to deal with those video adversarial examples and hence improve the safeties. Also, it helps us to understand the working mechanisms of those video recognition models, and it helps design more robust learning algorithms. So compared to the image models, attacking the video recognition models is much more challenging. As far as we know, the video data is in a much higher dimensions than the image data. So that means searching the adversarial perturbations in the video data actually is much more complex, and hence the attack efficiency are much lower than the attacking the image models, and also the high dimension of video data will cause very low attack success rates. And for the side of adversarial defense, the high dimensionality of the video data makes it not feasible for the adversarial training. So so that means if we want to generate video adversarial examples and also develop the defensive mechanisms, we need to find ways to deal with the high dimensionality of the video data. So there are two potential solutions to deal with the high dimensionality of video data. The first one is sparse attack. So here, sparse attack means we can, chat. Oh, yeah, if you have any questions, actually you can disrupt me and direct me.
Yeah, hi, Dr. Chen. Your background sometimes is a little bit disturbing. Yeah, I mean, there's maybe some voice. I don't know. Yeah, from there's quite some noise in the background, kind of.
There's some noise, but actually, no.
Yeah, I think maybe some kind of like object moving noise, something. Object moving, yeah. But right now it's very good. Right now it's very good. Yeah. Just right occasionally. Yeah, just occasionally.
Okay. Yeah. Okay. Sorry. So.
Yeah. No worry.
Okay. So I will continue now. So the first one is sparse attack. So sparse attack means we search the adversarial perturbations on a few video frames, so only on a few regions. So in this way, we can reduce the searching space and can achieve and can make the attack process more efficient. So the other solution is the transfer-based attack. So here, transfer-based attack means we can corrupting the adversarial perturbations on a substitute model, and then transfer the adversarial perturbations to attack the black box models. And here, the substitute models can be a white box model, or can be a model that's with a lower, which is not so complex as the target models. For example, we can try to generate adversarial perturbations on the image models, and then using the adversarial perturbations generated on the image models to attack the video models, something like this. So in this way, we can achieve a more efficient adversarial attack. So before I introduce the works, I firstly give an introduction on the two typical types of the attack. The first one is a white box attack. So under these settings, that means the structure as well as the parameters, so the models are accessible. So in this setting, it actually much more easier. And the second one is the black box attack. That means the structure as well as the parameters, so the models are unknown. Under this setting, the attacker can only access the output of the model. For example, the attacker can only access the logics or the hard labels or the probabilities, something like this, to corrupt the adversarial examples. So compared to the white box attack, the black box attack are much more difficult. So for attacking the video recognition models in the literature, the first work is the sparse video attack method. This method attacks the video recognition model under the white box settings. This work is published in the TrustML 2019. So actually, the main idea of this work is to generate the adversarial perturbations only on a few video frames. So in this way, it can generate the adversarial perturbations in an efficient way. And it then attacks the CNN plus RN models by propagating the perturbations to other frames with the recurrent neural network. And here is the overall framework. So actually, this method achieves the sparsity of the perturbations by using the L21 norms. So using this norm can help to generate the sparse perturbations. The idea is quite straightforward for this work. And here is the visualized results of this method. So from the left picture, we can see that's sorry. The first row is video frames with adversarial perturbations, and also the second row is also the video frames with adversarial perturbations. And the third row is generated adversarial perturbations adding to the these two video shots. So we can see that the generated perturbations are actually quite sparse. But actually, by adding these perturbations to the videos, it can fool the video recognition models. So the first work actually tries to attack the video recognition models under the white box settings, and it also there are some researchers try to corrupt the adversarial examples under the black box settings. So as we mentioned, that under the black box settings, the structure as the parameters of the models are unknown. So under this setting, the attacker can only access the output of the models by sending the queries to the models. So by sending the queries to the models, they can estimate the decision boundaries and hence to generate the adversarial examples. So for the black box attack on the video recognition models, the first work is published in 2019 in the ACM Multimedia Conference. So actually, the method I mentioned here are all very straightforward. So there are not too much theoretical new theoretical discoveries in these works. So for this work, the main idea is to utilize the tentative perturbations transferred from the pre-trained image models, and then participate the tentative perturbations into the patch and use the natural evolution strategy to rectify the gradients from these perturbations, and then use that to generate the adversarial examples. So here is our overall framework for this work. So the first step is to generate tentative perturbations with pre-trained image models. And the generated tentative perturbations here is the pixel-wise perturbations. So to make the gradient updates process more efficiently, the author participates the generated tentative perturbations into a subset of patches, and then use a black box gradient estimator to estimate the weight patch for the rectification, for the correction process. And then the patch-wise rectification weights applied on the patches to obtain the pixel level perturbations, and then apply a PGD to get the rectified perturbations. So here is the whole process. And the discover from this work is that actually the black box attack on video recognition models is feasible, but it requires a lot of queries. For example, if we want to obtain the attack success rate around 93% for targeted attack, it may require around more than 30,000 of query numbers. But for the long-targeted attacks, it requires around hundreds of queries to establish a success and also attack on the CNN plus LSTM model. So that is the discoveries from this work. So here is to visualize the results, and the left is the original video, and the right is the video with adversarial perturbations. So we can see that the perturbations is hardly it's very difficult to be observed by our human eyes, but it can mislead the video recognition models. So as I mentioned, that the previous works demonstrate that it is feasible to generate the adversarial perturbations of the videos under the black box settings, but the query numbers is actually quite high, so around more than 30,000. More than 30,000. That means it is not very efficient. So to improve the attack efficiency, so we propose a sparse attack method for the black box video recognition models. Actually, the main idea of our work is to reduce the query numbers by searching the adversarial perturbations only on a few video frames and also a few silence regions. So that means the first step is to select a few video frames to craft adversarial examples. So for this one, we call it as the temporal sparsity. And then for those selected video frames, we only searched adversarial perturbations on the silence regions. That means we only want to add perturbations on the foreground, the foreground of the video frames. So we call this as the spatial sparsity. By applying the temporal sparsity and also the spatial sparsity, we can reduce the searching space and make the attack process much more efficient. Okay, sorry, the slides has some Chinese here. here is the framework of the here is the framework of overview of our method. So the first step is actually first step is actually select a subset of the video frames that's which are important for the recognition. So we develop a heuristic rules to select a subset of the video frames, and then we detect the salience regions on the selected keyframes to search the Warsaw perturbations. So actually the whole process is like this. Firstly, the perturbation directions are initialized with the samples from the other classes that different from the class, so the clean video. So then we heuristically search a subset of frames from the clean video with the initialized directions, and the salience of regions detected from the selected frames are utilized to update the initial directions. So after that, the initial directions as well as the selected keyframes are updated iteratively to make the number of selected frames as small as possible. And meanwhile, we keep the perturbation noise lower than the given bound. So here is some visualized adversarial perturbations, and the first row is the original video frame, and the second row is the adversarial video frame, and the third row is a third row as the adversarial perturbation visualization result. So we can see that the adversarial perturbations are actually generated for the foreground regions, so the video frames. So our findings is by adding the adversarial perturbation on the selected foreground regions, actually we can achieve rather high attack success rates. And from the left picture, actually we can find that with both temporal and the spatial sparsity, we can reduce the query numbers significantly. And for success attack, the median query numbers for our method is around is around 12,000, which is much smaller, much lower than previous works. So that means the sparse attacks can reduce the query numbers and make the attack process more efficient. Okay, so so far, I have introduced the sparse attacks for the black box attack on the video recognition models. So with the sparse constraint, we can make the attack process more efficiently. But actually, it still requires around more than 10,000 of queries. So that means it actually still requires a lot of queries. So after that, we have investigated the transfer-based attacks for the video recognition models. So before I introduce the work of the transfer-based black box attacks, I firstly will introduce what is the transferability of adversarial examples. Actually, the transferability of the adversarial example is discovered in a paper which were published on the ICCV 2019. So in this paper, the author discovered that the adversarial examples crafted for the ResNet 18 can also fool the models for other models like the DenseNet 121 and also the QuickNet. So the authors named these characteristics of the adversarial example as the transferability of the adversarial examples. So that means the transferability of the adversarial example demonstrates the the feasibility of attacking the video recognition models by corrupting the adversarial example on the white box models. So for the transfer-based black box attacks on the video recognition models, the objective is actually to corrupt the adversarial example on one white box models, and then we leverage the transferability to attack another black box model. But there are some problems when we want to try, when we establish the transfer-based black box attacks. The problem is actually generates the adversarial perturbations are likely to overfit to the white box models. For example, like the results I show here. Actually, the results is copied from the paper improving the transferability of adversarial examples with input diversity, which was published on CVPR 2019. So actually, in this paper, it mentioned from this table we can see that corrupt the adversarial perturbations on the white box models can achieve very high attack success rate. For example, for the inception V3, it can achieve around 100. It can achieve 100% of attack success rate, but by using the adversarial perturbations on handcrafted on the inception V3 models to attack other models like inception V4 or inception red-let V2, the attack success rates will have a dramatically drop. So it will drop to around 5%. So actually the attack success rates are quite low here. So that means the generated adversarial perturbations are overfit to the white box models, and it less the low attack success rate on the black box models. So the key to improve the attack success rate on the black box models is to improve the transferability of the adversarial examples. And also, this is goal of our work here. Okay, so for the transfer-based adversarial attacks on the image models, I will introduce two typical ways to improve the transferability. The first one is the diverse input attacks. The diversity input attacks. For this method, it actually applies the random transformations to the input images at each iteration to improve the transferability. And the second one is the translation invariant attacks. So for this one, the objective is to make the adversarial example be less sensitive to the white box models. So they achieve this by optimizing the perturbation over an ensample of the translated images. So in both ways, they can make the generated adversarial perturbations less overfitting to the white box models and achieve high transferability. So actually these are designed for the image models. So that means actually for the video models, the transferability of the video adversarial examples have less been studied. So actually motivated by these two works, we studied the transferability of the video adversarial examples. Actually our method is based on the observation. That's the observation is that different video models actually have different discriminative temporal patterns. So the different discriminative temporal patterns make the adversarial examples have a very low transferability among different video recognition models. So how can we have this observation? Here we actually calculate the correlations between the importance order of video frames from different models. Here, what is the difference? So what means the importance of the video frames here? Actually, we do it in a quite straightforward way, because for video recognition models, it's different with the image models. Because for image models, we can visualize the important regions with the visualization tools, for example, like the CAM. But actually, for video recognition models, there is no such kind of tools to help visualize the importance of the video frames. So we design a quite intuitive way to calculate the importance of the video frames. For example, we remove the here. Actually, we remove the video frames, and for the first one is we remove the video frames and use the zero padding to fill the removed video frames and calculate the loss. So if the loss changes significantly, that means the video frames is quite important. So in this way, we can evaluate the importance of each frames. And then we order the importance of each video frames and calculate the similarities of the orders among different video models. So in this way, we can have the correlations between the importance orders of the video frames from different models. So from the results here, so we can see that actually the different video models have different discriminative temporal patterns. So, so if we want to improve the adversarial transferability of video adversarial examples, we must generate the adversarial examples which are less related to the discriminative temporal patterns. So to improve the transferability, we propose a temporal translation method. Actually, this method is shares maybe a similar idea with the spatial translation for the images, because the spatial translation for the image models, the main idea of that work is to make the generated adversarial examples less related to the discriminative spatial patterns. So in our work, we improve the transferability of video adversarial sample by making the generated adversarial example less related to the temporal patterns. So to achieve this goal, we propose to temporal shifting the video frames. So for the given input of the for given input videos, we generate a set of temporal shifted videos, video sets, and then we optimize the adversarial perturbations on the subset of the shifted video shots, and then we shift back the estimated gradient to the shift the gradient back to get the gradients, and in this way we can obtain the augmented gradient. So actually the idea is somehow like like to reduce the overfitting problem in a augmentation way, because here we augment the gradients from the subset of the translated videos. So in this way, we can make the generated adversarial perturbations less related to the temporal discriminative patterns. So we can get a higher transferability. And here is our objective functions. Here X is the input videos, and sigma is the adversarial perturbations, and Y is the ground truth labels. So and then we do a gradient aggregation, because we optimize the perturbations over a set of the video shots. So we need to aggregate the perturbations, the gradients on different video shots. So we aggregate the gradient in this way. Here, Wi is the weight matrix. So here, the weight of the weight matrix of W we use is the Gaussian from the Gaussian function, Gaussian kernel here, and in this way, we can get the aggregated gradients to generate the adversarial examples. And here is the attack success rate. Actually, in the overall algorithms, we have four hyper parameters. The perception boundaries. Actually, this one is not the hyper parameters. We can set it as other papers. And the iteration number, shift length, weight matrix. So the shift length here determines how many video subsets we use for aggregates the gradients. So so actually basically a larger L means we can have more translated video clips, but actually it will increase the computation cost. So that means the L we need to tune and to select appropriate L to our attack. I will show how L will influence the overall results later. So here is our results. From the result, we actually have several observations. Here, TT is our method, temporal translation. TT1 means the one-step attack. TT10 means the iterative attack. So from the results, we can see that for most cases, our method can improve the transferability of the video adversarial examples for most cases. And on both UCF 101 data sets and Kinectis 400 data sets. So actually, it demonstrates our method is quite effective in boosting the transferability of the video adversarial examples. Also, another good characteristics of our method is our method can be directly. Our method can be directly combined with existing transfer-based attack method. For example, like the TI translation invariant method, ATA, and also MI. So by combining with this method, the transferability of the adversarial examples can be further improved. So from the result, we can see on Kinectis 400 data sets, the performance can be improved around more than 20% for the iterative MI method here by combining with MI method here. So here I also show the results of the performance with regarding to the different shift length L here. So actually when L equals 0, it means it's the normal attack method. And a larger L means we can have more translated video clips, but the computation resources used for optimization, the perturbations will be larger than a small L. So actually from the result, we can see that when we increasing the shift length number, the performance actually have a very small improvement when the L is larger than 5 here. So in our work, we choose it as 5 here. And then we visualize the adversarial examples here. So the first row are blind video frames, and the second row are the adversarial frames. So actually, we can see that the perturbations very difficult to be observed here. So that means our method can generate the human inceptible perturbations, but can fool the video recognition models. This work is accepted by the IEEE 2022. So I have introduced the transfer-based video black box video recognition, transfer-based attacks for the video recognition models. And another work of also for the transfer-based adversarial attacks for video models is the cross-model transferable attacks. Actually, the main idea, the motivation for this work is that we want to make the computation resources be significantly reduced. So we want to generate the adversarial attacks on the simple models and use it to attack more complex models. So to demonstrate that it is feasible to generate that kind of attack, we firstly calculate the cosine similarity between the middle level features, so the image or the image models and the video models. Here we actually want to justify that the videos and the video models and the image models actually shares a similar middle level features. And because of that kind of similarities, we can achieve the goal of the cross-modal attacks. Otherwise, we cannot corrupt the adversarial perturbations on image models and use it to attack video models. So we firstly to justify our assumption here. So here, for the video frames, we extracted the middle level features of the video frames from image pre-trained image models, and also from the pre-trained video models. And then we calculate the similarities of the video level features. And here is the cosine similarities. So we can see from the result that actually the features between the image and the video models actually can be similar to some extent. So that means it may be feasible to achieve that kind of cross-modal attacks. And then we further do an experiment in this way. We generate the adversarial perturbations on image models, and then we using the generated adversarial perturbations to the video frames, and then send it to a video recognition models to see the channel-wise activation changes. So actually, from the results, we can see that the adversarial perturbations crafted on the image models will also change the channel-wise activation of the video models. So that means the adversarial perturbations on the image models can be transferred to attack the video models. So based on the observation here, we developed a method to realize such kind of cross-modal transferable attack. But there is one problem for the cross-modal attack here. The problem is that there is no free level labels for optimizing the adversarial perturbations. Because for the image models, if we want to corrupting the adversarial perturbations, we need to have the labels for the images. But actually, for our video data, we did not have the labels for each frame. So this is a major problem of this work. So to address these problems, we propose to optimize the adversarial perturbations by minimize the cosine similarity of the middle level features extracted from image models between benign frames and adversarial frames. So the idea of minimize the cosine similarity is is based on the motivation that actually the classifier's weight is highly related to the image features. So that means if we want to fool the image models, we need to make the features of the adversarial frames less related to its classifiers. So because we do not have the classifiers for the image models, because we do not have labels. So actually we use the features of the benign frames as the somehow as labels of the image models. So in this way we can craft the adversarial frames. So actually, this method is very simple and straightforward, but the experimental results are very, very good. And here is the overall framework here. So the whole framework is quite simple. For video shots, we firstly we generate the adversarial perturbations by minimize the cosine similarity of the middle level feature maps between the benign feature map and the adversarial feature maps. And then in this way, we can generate the adversarial perturbations for each frame. Then we integrate the frames to generate adversarial video frames, and then use it to attack the video models. Currently, this work is submitted to the CVPR 2012 this year, and is still under review. And here is objective function of this work. So as I mentioned, the objective function here is minimize the cosine similarity between the middle level features of benign frames and to adversarial frames. And here GLXI is the middle level features of the ice frame extracted from the image models. So as mentioned in previous works, in sample, different models can improve the transferability. So here we ensample multiple image models. For example, we can ensample ResNet, InceptionNet to improve the transferability. So we also consider the ensample attack. And here is the overview of the attack algorithms. So actually here is quite straightforward. So here is our experimental results. So actually we can see that although our method is very simple and straightforward, but the results are quite good. So we can see that for TPN15 and even without accessing any video models, our method I2V is our method, DR is the baseline method. So our method can achieve the attack success rate at more than 90%. So actually the results are quite promising here. So the conclusion from this work is actually by perturbating the features on multiple image models, actually we can generate the transferable video adversarial examples, because from these results, we can see that by ensample different image models for NL 101 and also NL 50, the adversarial the attack success rate can be improved significantly here. Also, we compared with another stronger baseline. The stronger baseline here is called ILAF. this method. Actually, the comparison here is not totally fair because ILAF is a fine-tuning method. That means it requires to access the video models to fine-tune the generated adversarial examples. But for our method, we did not require to access the video models. But from the result, we can see that for most cases, except for this one, TPN 101, for this case, the remaining 5 cases, our method achieves a much better attack success rate compared with this stronger baseline. So that means so our I2V attack method actually it can generate quite good adversarial video examples here. So for this case, our method actually works much worse than the ILAF method, and the reason is because maybe it's because for the TPN model, it actually can capture the motion features by aggregating the features from different layers. But actually, we corrupting the adversarial examples purely relies on the image models, which means we cannot capture so much action or motion features. So the generated adversarial examples works not as good as this one in this case. Okay, I will introduce our last work. So the last work is actually quite interesting work because for this one, our goal is to attack the video recognition models with split screen comments. So actually, an example I show is on the left side. So actually, the objective is to generate the bullet screen comments, and then by adding the comment to the videos, it can fool the video recognition models. So this work is quite different with previous works because this one is the patch-based attack. So what is a patch-based attack? Patch-based attack means that the generated perturbations actually can be observed by our human eyes. So for previous attacks, the generated perturbations cannot be easily observed by humans. So so this one is actually a different types of the adversarial attacks here. So the reason we generate a bullet screen comment to attack the video recognition model is because of the bullet screen comments actually quite common in nowadays because of some websites like Bilibili or others. So people are quite so the bullet screen comments are quite common, and people are maybe less conspicuous with these bullet screen comments. So actually for the image models, there are several existing patch-based attacks. But for image models, the patch-based attacks are mostly in the form of square patch. So which means this kind of square patch is easy to arouse humans' attention. So different with these works, we propose to attack the video models with the bullet screen comments. Here is the framework overview. Actually, here the framework is also very straightforward. So given input videos, we firstly generate the text comments with the image captioning models. So here we use the image captioning models to generate comments. We want to describe the contents of the videos, and then we use reinforcement learning algorithms to search the location of the bullet screen comments, and also to search the transparency of the bullet comment screens. And we have two rewards for the reinforcement learning algorithms. The one reward is the attack success rate, and the second reward is the average overlapping errors. Here we use the average overlapping errors as a reward because we do not want the bullet screen comments to be overlapped with each other, because if they are overlapped with each other, that means it will occlude the video contents, and it will affect people's watching of the videos. So we use this reward to avoid such kind of situation. And because of the overlapping reward, it also can limit the number of bullet screens, because if we add too many bullet screen comments, so they will occlude to overlap each others. So that means this reward will also limit the number of bullet screen comments. And here is our objective function. So as I mentioned, so we have two awards. The first one is the attack success rate. The second one is the IOU reward. And we use the reinforcement learning algorithms to search the parameters. For example, like the number of bullet screens and the font size. And we use the reinforcement learning algorithms to search the position of the bullet screen comments, as well as the transparency of the bullet screen comments. And for our algorithms, we actually have several parameters to tuning. For example, like the balancing factor here, lambda. The balancing factor lambda here is to balance the two kind of reward here. And the experiments are done on UCF 101 dataset and HMDB 51. And the target models we use here is C3D model, LRCM model, and also the I3D models. The metrics we use to evaluate the performance of our method is falling rates and average occluded errors. And here is our experimental result. Sorry, a little bit. So actually the conclusion we can draw here is when increasing the number and the font size, so the bullet screen comments, the falling rates increase firstly and then decrease. And while the error of the AOA keeps increasing, and also when increasing the value of the balance factors, the falling rates decrease while the AOA keep unchanged. And here is the overall results. Actually, the conclusion here is our method can reduce the AOA and the average query number by around 20% and 29% compared to the Bayesian hopping method. And also compared to the square patch, our BSC can reduce the AOA and the average query numbers by 37% and 29% here. So maybe I can skip here because time is limited, sorry. And here is the results of the visualize the results of bullet screen comments. So we can see that by adding the bullet screen comments, it can fool the video classification models. Okay, then we visualize the attention maps and see how the added bullet screen comment changes the attention maps. So from the results, we can see that by adding the adversarial bullet screen comments, it actually changed the attention to other regions. So it will make the model to produce wrong classification results. Okay, here is that's all. Thanks.
Okay, thank you very much. Thank you, Dr. Chen, for a great talk. it's indeed refreshing to us on the attacks on video recognition models. For the time limit, I have one quick question. For example, personally, I'm doing the defense on the image model, kind of like image classification model. What's your insight on the defense against those attacks on the video recognition models? What do you think?
Actually, that's a quite good questions because actually for the image models, the best way to defend the adversarial examples is by adversarial training. But actually for video models, we cannot do this because I mentioned the videos are high dimensional data.
Yes, very computational.
Yeah. So my opinion is for the adversarial defense for video models, what we can do is to train the models that can detect the adversarial examples.
I see.
Or develop some denoising models.
I see. I got it. Okay. Thank you again for Dr. Chin's great talk. Hopefully you can visit us physically in Tokyo to our Nihonbashi office in the near future when the situation lifted. Thank you very much.
Thank you very much. So if anyone have problems, can send me emails. Sorry to make you so long.
No worry about this. Thank you very much again. All right, next we're going to welcome our second guest, Dr. Gower. He's here. Swin is now a researcher in DeepMind, London. He received his master's degree and PhD degree in Swiss Federal Institute of Technology in Lausanne, EPFL. He had conducted many exciting research in the topic of adversarial robustness. We sincerely welcome Swin to come here to give us his talk. Hi, Swin. Can you share your screen?
Hi. Thank you very much for inviting me to the TrustML seminars. And today I'll be presenting basically my perspective on adversarial robustness. And this work is mostly around, the latest work that we've published at DeepMind in my group. And it's trying to gather together a bunch of observations that we've made and to try and distill them into some digestible pieces. And I'll be presenting two recent work and then trying to expand upon what are interesting avenues for future research in terms of robustness to LP norm adversarial perturbations. So the talk is mainly going to be centered around CFAR 10, and because that's where most of the research has been happening in that domain. But the techniques that I will present today are actually also working for other data sets like SVHN, CFAR 100. They also work to some extent for Imagenet as well. So just a quick reminder that the code is available online. Also, all the models that I'm going to talk about in this talk are available online at this GitHub repository. So feel free to go there and check it out. So before we start, I'd like to just thank a bunch of people at DeepMind that have contributed to this work to some extent. So here's the team, and there's a bunch of other people that are not even shown on this slide that I'd like to thank as well. So just to give a bit of context, so for those who are less familiar with adversarial robustness, on Imagenet, we can achieve actually superhuman accuracy. And this is a very great achievement, but these models that we have trained to achieve this superhuman accuracy, they're actually not robust against these imperceptible perturbations that we call LP norm bounded perturbations. And here's an example at the bottom taken from the paper by Goodfellow and others that demonstrates that you can take the image of a panda, add a little bit of noise that's barely visible, as you can see from the image on the right, and the classifier, which was correctly outputting panda before, is now outputting gibbon, and is outputting gibbon with very high confidence. And so this surprising observation around 2013 led to a bunch of, a new field basically in the area of machine learning and computer vision which is around understanding how to protect ourselves against these LP norm perturbations. And while you may think that LP norm perturbations are a very, very constrained, mathematically well-defined problem that doesn't arise in reality, I'd just like to think of it as it's not only a theoretical exercise. So that is, adversarial examples are actually not necessarily limited to images in the first place. So these happen also in language models, and they're not necessarily created by a malicious person. That is, they may arise by chance in the real world. And if they arise with sufficient, probability or chance, then maybe a system or self-driving system might fail. Secondly, we do want to increase the trust in machine learning systems and these neural networks. And so when the public hears that you can easily fool, classifiers with such imperceptible perturbation, they tend to, lower their trust in such systems. And one of the key fundamental aspects of trustworthy AI is that you want to expect your model to behave in this predictable way. And that's a very important topic in many ways beyond LP norm robustness. And also, finally, by building models that are robust to LP norms, we hope to learn something intrinsic or very important about building models that are robust to other things than LP norm. And just to give you a few examples here of very simple trickery that you can play on these vision models. On one hand, you have researchers at McAfee that tricked a Tesla into thinking that it should drive at 85 miles an hour instead of 35 by just making the bar of the tree slightly longer. And you have the stop sign, the famous stop sign on the right, where a bunch of stickers placed at correct positions would lead the classifier to think that this wasn't a stop sign. And by the way, if you have any questions, feel free to relay them to the organizers or to interrupt me in my talk. Then there's also many like downstream products that you can get from building models that are robust to LP norms. And in fact, we've demonstrated in 2 our works that you can leverage the techniques that you've built for this LP norm robustness in the latent space of a generative model, for example, or the latent space of an image-to-image model in order to build models that become robust to image corruptions that go beyond imperceptible perturbations. And so the first work, which is called Achieving Robustness in the Wild using adversarial mixing, was leveraging a style-GAN generative model and performing transformation of the latents in order to modify the image at the semantic level. So in this case, you could see a person that is possibly correctly classified as not smiling. And when you change the lighting condition of this image, suddenly the classifier thinks that that person is smiling with high confidence. And this may show that the model is relying on aspects of the data sets that are highly biased and this spurious correlation that may arise that, for example, people tend to smile more often when they're in the evening at a party or something like that. And then the other work, which has been accepted at ICLR this year, is around being just more robust to these common corruptions. So the CFAR10C and Imagenet-C data sets. And here we perturb the parameters of an image-to-image model in order to create more complicated corruptions of these images. And these corruptions hopefully cover the set of corruptions that we care about and that we want to be robust to. But again, this talk will be mainly around about LP norm perturbations. And if you have questions about this other work, feel free to keep them until the end. And I'll be happy to answer any questions about that later on. So just a recap, we're interested in solving the problem of creating models that are robust to LP norms. That is, typically what we mean is that we're gonna add a noise to an image, and this noise, the norm of that noise, it must be smaller than some threshold epsilon. And typically, in terms of which p-norm we use, in the literature, we tend to use either L infinity or L2 norms. There are other works that focus on L1 norm, for example, but this talk will be mainly around L infinity norms. One of the most successful technique that we have built to protect our models against these LP norm perturbation is called adversarial training by Madry and others. And really what you're formally interested in doing is minimizing what is called the adversarial risk. And what that formula says is that over your whole data set, you want to minimize a loss, but not only just the regular loss that you're used to, but a worst case loss. That is, you're going to perturb the input of that loss or input to the classifier in order to maximize the loss as much as possible within the allowed adversarial threat that you have. So in this case, the LP norm ball around the nominal image. And it turns out that if you do that correctly and you can actually maximize this inner problem here to optimality, then you can actually obtain the correct optimal robust classifier. And most of the difficulty into building models that are robust is actually to maximize that inner problem here. And typically what Madry and others proposed and Kurakin proposed is to basically start doing projected gradient steps in order to find this worst case adversarial perturbation. And it starts by choosing a random perturbation delta and then iterating over gradient steps and reprojections to the LP norm ball in order to find this worst case adversarial example. And finally, once you have this worst case adversarial example, you can input it in your regular training in the cross entropy loss. And there's been a tremendous amount of papers and hopefully progress in the domain of building these robust models. And here's an extract taken from Nicolas Carlini's blog, which demonstrates that the number of papers that talk about adversarial examples is increasing exponentially and is still increasing quite rapidly. But the question is really, do this exponential number of papers now lead to an interesting progress in terms of robustness? And it turns out that the progress, at least on the benchmark that people have cared about for the past 4 years, has been extremely slow. So if you look at this plot, which is extracted from the data from RobustBench, it basically shows two sets of clouds. One cloud is models that have been trained without extra data, and the second set of cloud in orange is the one that has been trained with additional data. Additional external data, so real data. And you can see that at least up to very recently, which was in the early 2021, the progress had stagnated for about 2 years, and we had barely any progress between the work on trades and the work by Rice on early stopping. Right? Second hand, you also had this very important jump in robustness by adding this additional extra data, but also that stagnated quite a bit. And so in this talk, I will just be talking about these latest models that are on the top left, which are, so you can see, for example, that I'll be basically talking about the fact that you don't necessarily need to use external data in order to achieve high robustness. And now we're slowly reaching up to 70% robust accuracy, whereas in 4 years we were at 44. So I consider that enough progress, but hopefully we can make some more progress to reach maybe in the 90s. So there are several challenges of robust training that basically hinder progress. The first one is around robust overfitting. So this is a phenomenon that has been observed by Rice and others, in which the robust accuracy will suddenly drop throughout training. And this is illustrated on the plot in the bottom left, which shows that as you train and you start lowering, you lower your learning rate. At that point where you lower your learning rate, you will have a high jump in the robust accuracy, but then suddenly this robust accuracy will degrade very rapidly on the test set. And we don't quite know why this exactly happened in the context of robustness, but it might have to do with the fact that, and I will see the next challenge, that you actually need a lot more data in order to build models that are robust. And this is validated in a sense when you add this extra data that comes from these external sources. So if you add this extra data, you can see that robust overfitting doesn't arise. And so this leads me to talk about the challenge of getting more data and having more data. And Schmidt and others and several also more recent work have demonstrated that you indeed need polynomially more data than standard training when you want to build models that are robust to these LP norm perturbations. And this is illustrated in that plot where instead of looking at the robust accuracy of our model against the standard CFAR10, we actually used a generative model to generate data for our model to train on, which means we have effectively an infinite amount of data to train on, and we generated 10,000 samples for the test set, and we kept the generative model basically continuously generating data for us. And we can increase the number of samples that we have from this generative model, and we should hope that by adding more samples, we would get to 100% robust accuracy. And you can see that you make early progress very quickly when you get to roughly up to 50K examples, which is the typical size of CFAR10. But after that point, you have some form of inflection where suddenly it becomes harder and harder to make progress against on the robust test accuracy. And in fact, you can increase the number of samples much further. We have increased it to 100 times this amount with 200 million samples, and you barely gain another 4 or 5%, which means you barely go above 70 at that point. And this goes to show that using more data is good in the short term, but I don't think it's the final solution, because we cannot afford to potentially train on this massive amount of data. Even if I were to generate 1 billion samples or 2 billion samples, I don't think we'll reach effectively 80% robust accuracy. The third challenge is around capacity. And so this was already observed in the seminal work by Madri, that when you use larger model, you in fact increase robust accuracy. And this has been also recently theoretically motivated by Bubek and others, where they explain the inherent relationship between the amount of neurons that you have in your neural network and the smoothness of your final model. And so you can also see it illustrated experimentally on this plot, where on the x-axis you have the number of parameters. So as we go more to the right, we increase the size of the neural network, and we have two lines. One is for when you use extra data, and one is without this extra data. And you can see that as you increase the number of parameters, you also tend to quickly saturate into a mode where your robust accuracy is much smaller than what you would want and what you would expect. So we can certainly build models that have 1 billion or 2 billion parameters nowadays, but this again wouldn't necessarily reach 80 or 90% robust accuracy on CFAR10. And so there's something else again that we need to discover here. And finally, there are some typical scenarios where you can actually show that, and Tsipras and others have done that, that there is indeed a trade-off between robust test accuracy and clean accuracy. But in our experiments, if you take the robust bench data, all right, the clean accuracy versus robust accuracy plot here, the clean accuracy on the x-axis and the robust accuracy on the y-axis, you can see that this trade-off doesn't seem to happen, at least for quite a while. And you can see that as you add more data and as you make your model bigger and as you have better ways of training your model, you can in fact increase both the robust accuracy and the clean accuracy. And that the trade-off really happens at the end there. When you start reaching, 92 or so % clean accuracy. After that, it becomes a bit harder to increase the clean accuracy. But even recent work from Raoul at EPFL demonstrated that, which is the helper-based adversarial training, I think, demonstrated that you can improve that trade-off quite a bit. And so it's unclear to me whether that trade-off actually happens for the LP norms balls that we are looking at, which are relatively small. And in fact, this trade-off, in my opinion, should not necessarily happen on Imagenet, where we have epsilons, right? The LP norm sizes that are very, very small, so 4/255. And so the first question I'm going to try to answer is whether adversarial training is all we need. Or in other words, is just, adding a little bit more data or increasing the capacity of our networks enough. And so this is the first work that I'm going to illustrate, which is about uncovering the limits of adversarial training against norm-bounded adversarial examples. And the motivation came from the fact that indeed there had been this very slow progress over the past 2 years, and we were very much interested in understanding the limitation of adversarial training. And so the contribution of the works were threefold. First, we actually did train a significant amount of models, did more than 18 ablation experiments, and we tried to evaluate all the models using the same consistent evaluation method, where each model was actually carefully checked for gradient obfuscation. So this is one of the things that have potentially hindered the field in the past, is that different researchers or different papers will do different sets of evaluation, and it's often hard to know which paper does slightly better. And here, when we talk about slightly better, even 1% makes a difference. And so the exhaustive work allowed to affirm and dispute a few of the prior works that have been published on the domain. And we were able to discover training setups that were able to significantly improve robustness. And I'll go over these in the next few slides. And ultimately, this led to an improvement in robust accuracy of more than 6% on CIFAR10 and more than 3% at equal model size. So the first discovery is that trades, which has been proposed by Zhang and others, does indeed do better than adversarial training. So there was this slightly earlier work from ours by Rice and others that demonstrated that you can actually reach the same performance as trades using early stopping. But if in fact you use early stopping with trades, you still get a boost in performance of roughly 1%. This boost in performance seems to happen almost exclusively for small data sets. So when we were using trades for Imagenet, we didn't see these boosts happen. So that's an interesting fact to try and remember. The second discovery was around model activation. This was already shown by prior work from Xi and others, but the main point here was to try again on CIFAR10, and we also discovered that indeed the ReLU unit or the rectified linear unit was not the optimal choice in terms of robust performance, and we were particularly impressed by the performance of the sigmoid linear unit, or SWISH, which seemed to perform better in all the settings that we have tried. However, we know that not all smooth activation functions necessarily improve robust accuracy. And so there seem to be, it's unclear to me exactly what creates this improved robustness from switch. And there have been a few recent work that have been trying to look at that. Last but not least, using more data. So here extracted from the tiny Imagenet, the tiny images data set really does improve robust accuracy, as we have seen from the earlier plot where we showed the dots in blue and orange. But what's interesting is that while the original work from Carmen and Uesato were focused on blending the number of extracted images from tiny images and the original CIFAR10 images at an equal proportion of 50-50, you can actually tune that threshold. And so you can use more examples from tiny images or less examples from tiny images, and that actually has a large influence on the robust accuracy. And depends obviously on the quality of the extracted data quite a bit. But in general, using more high quality data is better. Oh, sorry, that was not the last, so now that's hopefully the last. And finally, stochastic weight averaging seemed to improve significantly robust accuracy. And this is a technique that has been used way before in the standard training domain, but hasn't been really tried in the robust training domain. And this seems to be a no-brainer in terms of improving robust accuracy. And it seems beneficial no matter where you use it, whichever learning rate decay you're using as well. So when we combine all these techniques together, we actually get significant improvements over the state of the art across many data sets and across different LP norms. And that seems to, generalize pretty well from our experiments. The second question I'd like to answer is, do we actually need more real data? So, and I make the emphasis on real here. And so the first work is going to be around basically data augmentation, what type of data augmentation are helpful for robust training. And the second part of the work is going to go beyond data, like regular heuristic data augmentation. So the motivation here basically stemmed from our prior results, which basically showed that there is a substantial gap between the models that are trained with this extra data from tiny images and the ones trained without. And at that point also, the tiny images data set had been withdrawn. So it's actually not, you should not use it anymore in research because it contains offensive images. And so we're left here now with models that cannot use necessarily the same extra data as prior work. And we'd like to know whether we can actually close that gap without necessarily using this extra data. And so the contributions were to demonstrate that first, various data augmentation schemes can indeed be used to improve robustness. And this is somewhat contrary to what had been suggested in prior work, including our own prior work. Stochastic weight averaging is actually a key component that enables these data augmentation techniques to work for adversarial training, and that we were able to surpass the state of the art in the setting without extra data by almost 3%. And I'd like to go back a bit to the challenge of robust overfitting. So the key here is we'd like to avoid robust overfitting if possible. And so solutions to this problem that were basically investigated by Rice and others were, one, to do early stopping. So if you stop exactly after the change of learning rate here, you get a model that is reasonably robust. The second one is to use more data, as I've illustrated at the beginning of the talk. And the third one that was investigated was to use data augmentation. And we did also use data augmentation in the prior work without success. And what we can see here on the left on the right-hand plot is that for different augmentation techniques, the maximal robust accuracy that you obtain on your test set throughout training is actually the same, pretty much for all techniques except for mix-up. But as there's a big difference between how these curves behave after the change of learning rate, that mix-up and cut mix, so the green and red curve, are the ones that have the least amount of overfitting. So after the change of learning rate, they stay pretty constant. And so we're going to try and leverage this to our advantage. And so one way to try and leverage this observation is that we can indeed try to average model parameters or like try to do some form of ensembling of the different checkpoints that would happen after that change of learning rate. And so first we tried just using stochastic weight averaging without any augmentation. And you can see that after the change of learning rate here on the left-hand plot, the stochastic weight averaging, so averaging over the different weights of the network over time, will actually reach a higher performance. So that's a good first sign. And then after the change of learning rate, it will start to also go into this robust overfitting mode, but at a much slower rate than the blue curve. And so the hypothesis that stems from these two plots, and you can see, and also when you use extra data, you can see that you get this extra boost from using stochastic weight averaging, is that stochastic weight averaging is actually helpful to a greater extent when you can maintain the robust accuracy. And you can see that wherever you can maintain the robust accuracy in the blue curve, actually you keep getting better in terms of the averaged model robust accuracy. And so we tried different augmentation schemes with the addition with and without weight averaging. And those data augmentations that were actually suffering the least from robust overfitting, which I already had shown in 2 slides ago. So cut mix, mix up, and smooth mix, which is another one that we added here to the experiment. Those are the ones that actually benefit the most from weight averaging. And you can see it on this plot on the left, which shows the performance before weight averaging, so without weight averaging, which is the circles, and the performance after weight averaging, which are the squares. And you can see that smooth mix, which is this purple one, mix up, which is the green, and cut mix, which is the brown, are the ones that make the biggest improvement in terms of robust accuracy with respect to the non-average variant. And then in terms of absolute results, you can indeed see that from the standard pad and crop, cut mix does indeed improve quite a bit robust accuracy across different model sizes and across, and whether you're using extra data or not. And the caveat here is that when you start using this extra data, you need to increase your model capacity, because now you start adding more and more examples that are perturbed. And so your model will need extra capacity in order to cope with these extra examples. And if you do not have extra capacity, you actually hurt performance when you start introducing such data augmentation schemes. But overall, I mean, as we can see, 3% doesn't still quite close the gap in terms of using extra data versus not. And so they tend to be limited, right? These heuristic-driven data augmentation techniques are quite limited because they're hand-designed in some sense. And they tend to also produce samples that are not complementary to the training set, in the sense that they always take a training image or 2 training images and try to produce a new image from these, which means they're intrinsically limited in their ability to create a diverse set of new training images. And what we try to do is to measure basically the complementarity of these additional data augmentation techniques. And you can measure the complementarity, or it's a bit hand wavy, but like we can try to measure the complementarity by looking at the images that are generated by the data augmentation and try to find in some sort of feature space, and here it's the inception feature space, the closest image to either the train set or the test set or the augmented images themselves. And then we can start counting how many times my nearest neighbor is in the train set, how many times it is in the test set, and how many times it is in my own augmented set. And you would think that an ideal data augmentation technique or an ideal set of new data should have basically 33% everywhere. Because as you draw from if you draw from the true data distribution, you should be equally likely to be close to a training image, or to be close to a test image, or to be close to an image of the true data distribution itself. And this is illustrated by the top row of that table here, where if you look at the images that are extracted from the tiny images data set, the distribution among train, test, and itself is relatively close to 1/3, 1/3, 1/3. On the contrary, if you look at mix-up and the images that are produced and look at this distribution of neighbors, you can see that most of the images that are produced by mix-up are indeed close to the images in the train set, and rather far from images from the test set or the images augmented themselves. And so that leads to the question of whether we can do better. Is there a way to increase diversity and to improve complementarity to the train set? And this is the second work that is around improving robustness using generated data. In this work, we demonstrated that it is indeed possible to actually use generated data, potentially of low quality, to improve robust accuracy. We also leverage these higher quality generative models, so not only Gaussian models, as we'll show in the next slide, and showed that indeed the models that are better and the models that generate higher quality and more diverse images improve robust accuracy the most. And we showed that using these images from the recent diffusion or score-based generative models allow us to reach robust accuracy that are now matching the ones of using extra data. And the method generalizes well to CIFAR100 SVHN and to some extent Imagenet. So the strategy is relatively simple. It goes by taking the training data set, training first a non-robust classifier that will be helpful to generate pseudo-labels, and also training an unconditional generative model. These two steps can also be shrinked into one if you want to train a conditional generative model. But then the idea is from the unconditional generative model, you're going to generate a number of images. You're going to pseudo-label them with your non-robust classifier that will create a new generated data set. And then you can blend your training data set with the generated data set to train your robust classifier. Similarly to what we've done with the external data, where instead of using generated data sets, you would use the tiny images data set. And so the initial motivation stemmed from this observation that we've made, where if you actually take random samples that are generated by a conditional Gaussian fit over the CIFAR10 training data, so this is a very poor quality generative model. And you can see these images here on the right. That's an image of a car. You can see that it is very bad quality. You can barely distinguish it as a car. But if we add these samples and we try to blend them as optimally as possible, and that means actually taking 20% of our batch being these generated images and 80% being the original CIFAR10 images, then we can actually improve robust accuracy by 1%. And again, like 1% is quite significant when you think about trades versus adversarial training. So trades is also improving adversarial training by roughly 1%. And so this motivated us to look at these more complicated distribution or generative models. And before that, we tried to understand also why this seemingly bad random data was indeed benefiting robust accuracy. And you can actually demonstrate obviously in some very extreme scenarios, that if you have a robust an accurate pseudo-labeling mechanism, and that's the case on CIFAR-10, right? So we can get classifiers that do well over 95% on the CIFAR-10 test set. And two, you can generate, and the most obvious condition is obviously two, if you can generate images that are close to the real distribution, then obviously that's enough to improve robust accuracy. And that's really in the mode where you have limited capacity of your model. But as you increase the capacity of your model, you can start using generated samples that are of low quality. And the reason why is that, one, adversarial attacks are unlikely. So typically so if I generate a random image from the generative model and I ask the pseudo labeler to label it, it's very unlikely that this image will actually be by chance an adversarial example. And the second condition, or the third one here, is that generated samples should cover the manifold of real images. And so if you think about the Gaussian generative model, which actually has, it can actually generate by chance any image, really. It does cover the set of all real images. And so there's a non-zero chance that at some point it will generate an actual image that looks very close to a real image. And that image hopefully is complementary to the training set, doesn't appear in the training set. And you can leverage that to improve your robust classifier. And so there's really this trade-off between good quality of the generative model as well as the capacity of your robust classifier. And you can somehow trade off the two, which is interesting. And so if we go back to our table of nearest neighbors, you can perform the same experiment where now you take your generative model and generated data and you measure to which image you're closer to. So train, test, or the generated data itself. And you can see here that for the models we considered, all of them actually provide more complementarity to the training set. So mix-up, basically 90% of the images of mix-up were mostly close to trained images. But if you look now at the diffusion model, we get very, very close to the distribution of the extra data that would come from real images from the tiny image data set. And so that's very promising, and that leads us to perform basically the same experiment we did for the Gaussian generative model, where we start now introducing in different proportions, different amount of generated data from 4 different generative models. So here we tested the VDVAE, Big GAN, StyleGAN, and the diffusion model. And we can see that the 2 models that indeed have higher quality as measured by inception score and the FreshNet inception, FreshNet, well, whatever distance, they tend to produce, again, they tend to help a lot more with robust accuracy in terms of improving it. And the diffusion model is really the best model here, right? So, and that's maybe the quite surprising part, is that if you look just at the inception score, the StyleGAN and DDPM are indeed very, very close, also in terms of FID. Even the StyleGAN slightly better than the diffusion model, but the diffusion model seems to provide a better distribution over these neighbors, hence provides also better robust accuracy. And so, sorry for the rather large table of numbers, but now if you do actually add data from this diffusion model across these data sets and across these different norms, you always get an improvement in robustness. And really, there are 2 columns I'd like to highlight, two rows that I'd like to highlight. The first one is that is the last row of the first section, where if we use a lot of generated data, here we have generated 100 million extra examples from the diffusion model, and our model is of high capacity, then we get 66% robust accuracy, which indeed surpasses even the same model size using external data. And so the good news here is that we can actually now get rid of tiny images. We don't need it anymore, and we shouldn't use it anymore. And we can actually use this generated data to improve robustness. And then the last section, which is also interesting, is trying to apply the same technique to Imagenet, where here we saw that we could improve robust accuracy by roughly 1%. And there might be multiple reasons for it. So in one case, we are able to improve it by 8% for CIFAR10, and in the case of Imagenet, only by 1%. And one of the reasons is that, well, we might need even bigger capacity models for Imagenet, which are bigger images, but also the quality of the generative model Imagenet are worse in general. So if you try the Turing test on generated images versus real images on Imagenet, most people can still tell which images are generated and which ones are real, which is not necessarily the case for CIFAR10. And so that begs the question now of whether we're done with LP-norm robustness on CIFAR10. And I kind of will let you think about it. So I won't try to influence your decision here or your answer. But there's really, to me, 4 questions that are fundamental. Is the first one, is there a theoretical limit, or can we actually reach 80% or more adversarial accuracy on CIFAR10? And it does seem that currently using more data and just more capacity might not quite cut it. Possibly with this new data coming from generative model, we might be able to use significantly more data, and by pulling together multiple computers and building models that go beyond the 1 billion number of parameters, we might be able to reach 80%, but it doesn't seem to be a sustainable solution to go to 90%. And so there are basically 2 avenues that could be interesting in the domain. Is one, think about new architectures. So we've seen recent work looking at these adaptive test time architectures, which try to perform some computation at inference time. So these could potentially have the effect of increasing capacity, without necessarily increasing the number of parameters. And so those seem to be promising. The big problem here is that we don't know yet how to truly evaluate such models. And so we might be led into thinking those models are robust when maybe they are not. And the second aspect is around changing the training procedure. So obviously adversarial training as presented by Madry makes a lot of sense. But given that we're capacity limited and data limited, then maybe other losses and trades kind of hints at possible better trade-offs, right? Could be more appropriate. And so that's kind of the questions that I wanted to raise, and this concludes my talk. All the experiments are in these papers. All the code is available online for both PyTorch and JAX. And feel free to reach out directly to me if you have any questions. So yeah, I'd be happy to take any questions if you have any.
Thank you very much. Oh yeah, in the chat box there is a question.
Okay.
The total robustness achieved by the team is really impressive. Yeah, you can see.
Yeah, so I can read it maybe. So
Sure.
so there's one. So the total robustness achieved by your team is really impressive. It seems that you have. It seems that we never introduced new knowledge into the adversarial training in Rebuffy et al. Since we generate extra data only based on original data. Why can't the current classifier take full advantage of the original data set? Or does any implicit knowledge from the generative model helps adversarial training? This is an excellent question. And in fact, this is exactly the question that we're interested in answering. It seems very counterintuitive because from an information theoretic point of view, we didn't change anything, right? The fact that you build this generative model and then generate extra data doesn't add new information. It doesn't add new data to the, or new information about the training set, really. And so it seemed that it should be possible for the classifier, given enough capacity potentially, to improve robust, like basically to do the same job as this two-stage process where you generate and then train. And yeah, so there's quite something to it, and it might be due to maybe hinting at these new architectures where diffusion architecture is significantly different from a standard generative model, in the sense that it has this multi-step process in order to generate images and also for training. And so maybe it has more capacity in a way, like in terms of computations. And it takes a very long time to generate these images than the standard classifier that we have used. So it's possible that better architecture would just do well, and you don't need to do this two-step process. There's a second question. So I'll read it. It is clever to have the idea of identifying the worst adversarial examples. In the first place, add them to the training set. But this idea builds on knowing restrictions in the search space of adversarial example bounded LP norm. Practically would be preferable to have a generic defense, whereas robust against various attack methods instead of problem-dependent defender. How would we push towards a generic defender? Again, I think you're hinting at like basically the Pareto of research, like the front of the research field. There's multiple things. So one is obviously LP norms are a very practical setting. So we know very well they're defined, and increasing robustness in that setting makes sense, in the sense that we can actually test these hypotheses around model architecture, generated data, and so on. But in the end, you would like to be robust to something more meaningful potentially and semantically more relevant. So the examples of the person that suddenly goes from smiling to not smiling just because I changed the lighting condition. And really being able to build basically the perturbation set. So be able to learn the perturbation sets from data seems quite a promising area of research. And leveraging potentially generative model, which seem to be quite good at understanding the distribution of the data, could be also a possibility in terms of making models that would be robust to something a bit more useful than LP norm perturbations. In the situation where you want to be robust to multiple LP norms and you don't know which ones and you don't know which epsilons potentially, I think looking at potentially adaptive defenses, so ones that will actually not necessarily do well in the initial deployment, but as they see more adversarial examples or as they see different kinds of norms, they will actually adapt to it quickly. So this is a possibility here. There's a third question. It is very interesting to see that more generated data is able to improve robustness. Even generated data is of low quality. Could you give us more intuition and explanation about this phenomenon? Yeah, it's probably that I didn't explain it very well in the slides, but think about the worst generative model. So the one that would generate basically uniform over pixel values, kind of. So that model will mostly generate bad images, but it might by chance generate a real image. So there's nothing preventing it from generating a real image or an image that would be close to the true image distribution, like an image manifold. And so if you take that perspective and now you say, I'm going to have infinite compute and infinite capacity on my model, then I can let it run forever. At some point, I will have covered all the images that are real. So my generative model has this non-zero sense of eventually covering these images. And my model has enough capacity to actually memorize all of this. And my pseudo labeler is of good quality. So of all the real image that I've seen, 95% of them are actually correctly labeled. Then there is basically a chance that your robust classifier can get also 95% robust accuracy. So that's kind of like the reasoning behind this. But yeah, so it's very hand wavy again. It's not very thorough, but that's the way I think about it. And so it really means that capacity can play a big role when you have worse generative models, but you really want both. Like you want a better generative model and a better higher capacity model if possible. Yeah, so I think that's it from the different questions.
All right. Thank you again for Sven's great talk. Hopefully in the near future, you could visit us in Tokyo physically. Oops, there's another question. Yeah, come
happy
here.
To, happy to answer.
Sure.
So thanks for the talk. Shows that training with more data can gain a big robustness improvement, but practically I think it is a bit computationally heavy. You have some insights about whether it is possible of training something to training with less generated data for training that can improve adversarial training. Yeah, this is exactly, I mean, this goes exactly to the point of what I was saying before, which is if you have a generative model that has the capacity to generate real images, but generating this image is very rare, then you're going to have a lot more images or sample a lot more images and train for longer and have higher capacity model in order to get gains in robustness. And so really here, if you want to use generated data, the best bet is actually to improve generative models. But again, like, so it seems to be shifting like the problem from training models that are robust to just training generative models that are better. And that's a fine, you know, it's fine to switch fields, I guess. So, so yeah, it's a like, I don't have a good, you know, a good answer to this, in the sense that if you want to use less generated data, you probably want better generated data. At that point, that seems to be the case. Obviously, again, there is a way, like my gut feeling says that even with the CIFAR-10 data set itself, you should be able to improve robustness to at least the level that we get with generated data. It's just we don't know which model architecture or which training mechanism should be used for that. So again, like, but that means there is something to do, which is exciting.
All right. Thanks again for Sven's Gower. You seem the talk is very interesting. Many people ask many questions related to your talk. Hopefully, in the near future, you could physically visit us in Nihonbashi office in Tokyo. We are in the center of the Tokyo. Yeah, definitely we will hugely welcome you. Thank you again for your great talk. Okay.
Thank you very much for inviting me. Thank you.
Thank you. Okay. Now this is the end of the first Young Scientist seminar. Hopefully we can see each other when the situation is lifted. Bye-bye.